We are running about 10 to 15 minutes behind. I'd like to introduce our final individual speaker, is Evan Beard. Evan is the CEO and co-founder of StandardBots, where he's building vertically integrated AI-native robotic arms and a robotics platform for learning through demonstration. He was previously recognized on the Forbes 30 Under 30 list and the Business Insider's list of them as one of the most inspiring and influential people in New York tech. He graduated from Duke University, where he studied economics and computer science. So welcome, Evan.
Hey everyone. So we make AI native, vertically integrated robots for automating manufacturing tasks. Just a minute about us. We make the hardware, the software, and the AI stack. We're growing really quickly, and we've raised about $65 million from General Catalyst, Amazon, Samsung Next, and some others. So the problem we're solving is robotics today, most robots are just replaying motions. They're just running through the same movement again and again. And you almost have to be a software engineer to program the robots. So the interfaces are very confusing. You have to memorize a lot of things, and they're not capable of automating many of the tasks out there. Even for the most common tasks to automate with robots, the deployment rates are closer to 10%. These are some of our robots. There's a robot with Jensen. We do kind of traditional tasks like welding and machine tending and other things like that. And I mentioned we're vertically integrated. We've designed our own motor controller, our own encoders, our own motors. We assemble here in New York, so we've really tried to rethink robotic arms from the ground up. And we have better specs than a lot of the competitors, and we've tried to make them really simple and easy to use, like an iPhone-type experience. But the real question and the focus of our company is on being able to automate a lot more. And the question we ask ourselves a lot is, why can robots do so little today? And the answer to that is really because there's so much variability in the tasks that customers want to do. And that can be the color and the shape and the type of objects, or it could be the environment and the lighting changing, or it could be they make one thing one week and something else the next week, and the program has to slightly change. iPhone's an example of this. So the US Commerce Secretary recently said that Tim Cook said that the only reason the iPhones aren't made in the US is because he doesn't have the robots. And obviously, he didn't mean the hardware. He meant the software that the robots run isn't sophisticated enough to assemble iPhones. And there are so many tasks like this that we see out there, where if the software could be smarter, you could perform the task. We're starting with manufacturing, but obviously across industries. This is from a McKinsey report. There's hundreds of billions of dollars of tasks that we can automate. And so the big change that's happening right now in robotics is this move to end-to-end AI models. And we've seen it in self-driving. So all the major self-driving companies are moving from just using AI for perception to find, say, the lane markers and the stop signs and those kind of things, and having rules-based or procedurally written code for actually driving, to a world in which the model is actually outputting trajectories, one or more trajectories, and they're choosing one of those trajectories and executing it on the vehicle. The problem with the procedural way is you write rules for one intersection, and then they kind of conflict at the next, and it becomes very hard to write a self-driving program that way. Robotics over the last 10 years has been a lot of the same. There have been some models for detecting objects, but just detecting an object isn't enough to get a job done in many cases. And so we're seeing the shift to end-to-end models where the model is taking as input the camera data, the tool position, the gripper state, and it's actually outputting a trajectory for the tooltip for how to get that job done. These are some examples of this. I'll talk about a few ways that we collect training data, but this is a handheld device that we've made to collect training data, and on the right, it's operating autonomously. The really cool thing about this approach is because it's looking and creating the trajectory in real time, it can react. So on the right, the user actually moves the can, and the robot can immediately react to that movement. And it's almost like it feels like it can think sometimes as we're training some of these models, where when something goes wrong, something slips out of the gripper, it can respond instantly. On the left, you can see it's robust to the location of the can, the type of the can, the location of the cup it's pouring into. It can align the spout so that it pours on the right side of the can. And you don't have to write any lines of code for any of this. You just demonstrate the task, and it learns how to do that through the demonstration. So really, really cool stuff. Here's a couple other examples. Battery insertion on the left. We're finding that bimanual setup is really helpful because one robot can hold the item or help to reposition it, while the robot on the right is interacting with the world, like on the left video for the battery insertion. Here's a couple ways to collect training data. This is using mini arms. So the mini arm is often a kinematically scaled down version of the bigger arm. This is really great if you want to control all the joint positions, so you can avoid collisions really well this way, because you have full control over the whole arm and where it's moving. I was actually, a robots were in a movie with Nicole Kidman called Baby Girl. This was in that movie, which was kind of cool. Another way to collect training data we've tried is with a handheld device. So we built this device, and it has a force sensing on it. It has an interface that can support lots of different types of end effectors. So you can plug in the end effector, control it with a trigger. It's all electronic and records all the training data you need. We find this is good if the end effectors are light. If you start to get a heavier end effector, then it becomes kind of onerous. So joke you can tell our data collectors because their right arm's really big. So they're carrying these like huge grippers all day. This is another way that we like for collecting training data, where our tablet localizes itself and the tooltip moves in sync with the tablet. So this is a really simple way to collect training data because you can do it at the customer site. You don't need a lot of equipment or external tracking. We find that with movement scaling with this approach, you can train with really dexterous tasks. So similar to like the Da Vinci robot, obviously. Da Vinci robot, the surgeon moves an inch, and the robot actually moves a fraction of that. So with movement scaling, you can switch to like a fine-tune mode and demonstrate more dexterous things. And then finally, we're pretty excited about collecting data through VR, AR type approach. So those are different ways to collect demonstrations. For where we are today in robotics is really just about short horizon overfitting. So we haven't seen any kind of foundation model be able to generalize between robots or between tasks super well. We do find that the foundation models are having lots of examples help for different, as a starting point, but you're really training a task-specific model and overfitting the model to that task. The biggest advantage of this approach is you can now automate tasks that weren't possible to automate before, right? And that's a lot of the work that we have out there, like assembling iPhones. So that's a really big deal for customers. We also think that customers will see a better ROI because it's just easier to program a task when you just have to demonstrate it and there's no code to write and you don't need experts to be in the loop on that. And being able to correct mistakes in real time is a big deal as well. These are some of the robot features that are needed for this kind of approach. So you really want to have a good low latency, high speed interface for real-time position and gripper control. Not every robot has that, not every gripper has that, but the model streaming commands out for the robot and the gripper, so that's important. You really want to have good impedance control on the arms so that you can interact with the world without moving to either the max force the arm can apply or triggering a protective stop. A lot of the arms out there have really tight parameters around their collision detection, so if you hit something, they trigger a stop. And then having bimanual support's another thing that's pretty useful for this type of control. This is what one of our programs look like. We've made it so it just reads like a story, and each step encapsulate all the logic that happens inside that step. And for us, AI is a step in this program. It's a skill in the story that we're otherwise running. So we're using classical methods to do everything that you can use classical methods for, and AI only for the parts that require it. In terms of simulation, we think it's really great for these reasons, but not every task requires it, and obviously we find that lots of real-world customer tasks are hard to simulate. And this is our vision, is to be the platform for applied AI in robotics. If you try to deploy these models today, there's a lot of reinventing of the wheel. It's a lot of work to create your own pipeline to collect the training data and upload it to the cloud, train the models, organize your data. deploy the model. So we're trying to make that really simple and easy. And then these are just some shots of collecting training data. You want to be able to annotate often with human readable text, different segments of your task, and then manage and deploy your models. So just wrapping up, almost no robots today are running these type of end-to-end AI models. It's really, it's just the beginning of this shift. And we think it's going to go from almost zero to this is the mainstream way that all robots are programmed over the coming years. We think our ROIs will be higher. We think that every single quarter, more and more tasks will be possible. So all the advancements in LLMs, like GRPO from DeepSeek, that's all directly applicable to robotics, just like it is to LLMs. And we think next year we'll start to see tools where it's really simple for production situations to train these models and deploy them. But thank you all for having me.
And I don't know if my mic's on, but it is on. I just wanted to thank you for coming. So I wanted to, if you go through the Automate show, which is the leading, taking the whole other approach here. If I go to the machine tool industry, I want to look at factory robots. We've been talking about AI this whole time, but if you go through the Automate show, you're going to see this guy's company. There's one coming up. It was there last year. It's different in two ways. One, robots are built here in the US, designed and built completely with his own motor. And two, he's using biomimicry and AI in a way that other people haven't. And I think the thing that most people wouldn't realize, there's a long history of dead bodies in trying to program robots. And sorry, billions of dollars have been spent by luminary names who've invested in companies like Vicarious, which you know well. So I think this is really different, and this is a good space to watch because he's jumping on a new platform and going forward. So two big differences. Thank you very much for coming.